Hello, this video is a short introduction on photoacoustic imaging. I designed this presentation originally for the university seminar Methods of Physics in Biology and Medicine at the University of Heidelberg. But I think it turned out quite nicely, so I decided to share it with you as well. The major breakthroughs of PAI are still quite young compared with other imaging techniques, so you might not even heard of photoacoustic imaging before at all. I will start with the basic working principle of PAI to get everyone on the same page. After that, I will give you a tour through the history of PAI, and I will introduce you to the physical description of the technology. Then we will have a look at the instrument types for PAI and at prominent examples of what has been achieved already. In the end, you will get some glimpses where the journey might lead to in the future. Now, let us get into the topic. What is photoacoustic imaging? As the name already implies, it is an imaging technique based on light as well as sound waves. This has some inherent advantages because the two types of waves behave very differently in media. One very basic example of photoacoustic measurements that you probably all know is for locating thunder. We see a lightning strike and we start counting. When we finally hear the thunder arriving at our place, we stop counting. By this, we can measure the distance to the lightning strike because we know that the thunder traveled with the speed of sound, since it is a shock wave of spontaneous air expansion, and it emerged from the immense heating from the lightning. In photoacoustic imaging, we apply this principle to biological tissue. We use a very short laser pulse and shine it onto our sample. It has exactly the right wavelength that it is absorbed by the structure that we are interested in. Due to the fast heat uptake, it comes to thermoelastic expansion, which travels as an ultrasonic pressure wave through the sample. Now we can set up detectors like in conventional ultrasonic imaging and reconstruct the structure of interest from the time delay of the waves and their intensity. This mixture of optical and acoustic measurement has some great advantages. First, high contrast, since the detected signal is exactly emitted by the structure of interest and not backscattered from everywhere like with conventional ultrasonic devices. Second, the method is much more robust against diffusion of light compared to optical-only imaging, because the light does not need to be perfectly focused here, and it crosses the tissue only once. Therefore, we can achieve greater imaging depths. Now that we have a first understanding of what PAI is, let me give you an introduction how it was developed. The photoacoustic effect that light translates into pressure waves when it is absorbed was already discovered by Alexander Graham Bell in the year 1880. He used this effect to invent the photophone, where sound is transmitted by light. Here on the left, a light ray is modulated by a mirror which deforms due to the pressure waves of the spoken words from the first person. Here on the right, the light hits the receiver. Bell used a selenium receiver the material has the advantageous characteristic that it converts temperature directly into resistance. Thus, the optical signal is translated back into an electrical signal, which then again can be used to transform it back to an acoustic signal by a speaker. His invention sadly did not take off due to the development of the radio, which was more convenient since you didn't have to shine a light between receiver and sender. Although one could argue that the modern glass fiber internet is a successor of Bell's photophone. After this, in year 1943, a German scientist named Luft made use of the photoacoustic effect for spectral analysis of trace gases. One can see a light source shines onto gas molecules through a filter that only lets through one wavelength at a time. If the gas in question is able to absorb this wavelength, it heats up abruptly, sending a pressure wave to the microphone. Then we can derive from the average intensity of the signal how much this wavelength contributes to the absorption spectrum of the gas. For the first development of an imaging technique for human tissue instead of gas, we have to wait some more decades until 1993. Here, the first optoacoustic measurement of a human finger was done. In the experimental setup, you can see that the laser pulse is transmitted via an optical fiber, and the ultrasound signal is measured by a concentric piezoelectric polymer transducer surrounding the optical cable. In the detected signal, one can see the high potential for good depth resolution of this technology. From there on, the race was on, and several competing researcher groups kept improving the technology. In 1998, the first three-dimensional photoacoustic imaging results were published already. This was achieved by rastering over a sample. In the experimental setup, one can see how the sample is moved by the 3D translation stages. Nowadays, usually the laser and the ultrasonic receiver are moved instead. To understand the possibilities and limitations of PAI on a more detailed level, let us now move on to the physical description of the signal creating process. At the core of the signal stands that absorbed light is transformed to a pressure wave. The delivered light at a certain time, at a certain point in the tissue, can be described by the irradiance. For our process, we are interested in the total energy uptake from the laser pulse at a certain point, which is the integral over the length of the laser point times the absorption coefficient, which tells us how much energy is absorbed. Where the total energy that arrives at a certain point, described by the integral, is also called the fluence. The energy uptake corresponds to heating. We assume that we tuned our laser in such a way that only conversion to temperature rise takes place. So we do not have any other unwanted effects like chemical reactions or photo disruption, all the energy is translated to heat. Therefore, we can express the temperature rise through our laser pulse by this. This temperature increase is instantly translated to a pressure wave. To understand this, we start with the total differential of volume for a thermodynamic process with constant particle number. You might remember this from thermodynamics lectures. Now we make the assumption that the laser pulse is so short that for the duration of our dynamics there will be no significant volume change. All energy delivered as heat is translated to pressure. If we look at the formula, we see that the change of volume with growing pressure as well as the change of volume with growing temperature are general material properties. Dividing by the volume, we get the thermal coefficient for volume expansion and the isothermal compressibility. Now we have the relation between the temperature change and the pressure change. Now we just need to insert the temperature rise induced by the laser that we derived before. And we get this relation between the initial pressure rise and the laser pulse. We can see that most parameters are independent of wavelength and constant in the ultrafast dynamics of the laser pulse interaction. Therefore, we summarize them into the Grüneisen parameter. And now we have a quite concise formula which tells us a lot nonetheless. We can see that for a stronger signal, we can either choose a stronger laser, but this is confined by what the tissue can take until it is damaged, or we find a wavelength where our target absorbs light more efficiently. And we can see the big difference to optical only or ultrasonic only measurements again. The signal comes from absorption instead of reflection or transmission. Therefore, the contrast depends mainly on the difference between absorption coefficients of the target and the surrounding tissue. Now that we know that the absorption coefficient is the decisive factor for PAI, we can take a look which types of targets are detectable at what wavelengths. In this figure, the absorption spectra of different components of biological tissue are shown. You can directly see two prominent lines, the lines of hemoglobin from red blood cells. Interestingly, we can observe the absorption coefficient of HbO2 and HbR, so the reduced hemoglobin and the oxygenated hemoglobin. They differ for certain wavelengths. Therefore, with two lasers at different wavelengths, it is possible to measure blood oxygenation. The same is true for myoglobin, the transporter of oxygen in muscle tissue, MbO2 and MbR. One can also identify potential obstacles in the imaging. Melanin and water pose a problem. Due to the high melanin concentration in the skin, it directly already absorbs a lot of light before even the interesting imaging part starts, which also limits the strength of the laser, since the melanin will heat up much more than the tissue below. And additionally, water creates noise everywhere, and depending on the absorption strength of the target, this could be a problem for the contrast. In the second figure, you can see examples where PAI was realized for different prominent targets at very different wavelengths, which I find very impressive that over such a large bandwidth of wavelengths, this technology is useful and used. After this theoretical approach of what targets are feasible, let us move on to the technical realization of imaging devices with PAI. There are mainly two groups of PAI instruments. The first group are photoacoustic microscopes. There, a laser sends a pulse to a target and a single ultrasonic transducer is used for detection. There are versions like this one shown here, which mainly focus the laser to achieve a high resolution, actually quite similar to fluorescence microscopy. And there are versions which mainly focus the emerging ultrasonic pulse to achieve high imaging resolution, called AR-PAM. The ultrasonic waves are more resistant to diffusions, therefore these devices can achieve deeper imaging depths, but they are harder to focus, which leads to a lower resolution. To create 2D images, then a sample is rastered. The second group of photoacoustic imaging is photoacoustic tomography. Here, the whole sample is homogeneously illuminated and a whole array of ultrasonic transducers records the emerging signal. In this case, a similar imaging reconstruction like for MRI is performed. This way, imaging depths of up to 7 or 8 centimeters can be achieved by now. And as you can already imagine, there's always a trade-off between the imaging depth and the resolution. The imaging depth is typically limited by scattering, refraction of light and sound, and the absorption of other substances than the target. The resolutions that are at the moment possible lie for the photoacoustic microscopy somewhere around 0.2 micrometers and are mainly limited by the wavelength and the aperture in sound or light, depending on the technique. And in the photoacoustic tomography, it is mainly limited by the bandwidth of the ultrasonic transducers and the size of the ultrasonic transducers, how many you can put in an area. And the best resolutions here are about 0.1 millimeter. Since I want to offer a critical review, let us also have a look at the other constraints of these. One limitation arises from the need to be in physical contact with the sample through a coupling medium. This physical contact, coupling, or immersion of the sample can be quite impractical for some applications. For example, often in clinical applications, if you want to use this on humans and do a full body PET, then it would be quite inconvenient to submerge the person into water for the contact. And the absolute quantification of the received signal poses a problem, apart from the physical contact. The intensity of the measured wave is not only dependent on absorption, but also attenuated by the tissue in between. Although this is a very common problem of solely optical imaging techniques as well, this does pose a problem for quantitative science and analysis. But despite those limitations, the technique certainly has its justification in many use cases. Let me show you some examples of what has been achieved already with PAI. The first example I present to you is a tomograph for small animals from 2017. In the sketch of the setup, one can observe the unfocused laser beam which illuminates a cross-sectional disc homogeneously. This is achieved by a special cylindrical lens. The signal is then registered with a circular array of ultrasonic transducers that has an acoustic focus to the illuminated plane. They use two lasers with different wavelengths with a short delay such that they can detect blood oxygenation. And here you can see the blood oxygenation levels in the main arteries of a mouse brain. In the gray area, the mouse was exposed to an atmosphere with less oxygen. But this tomograph has also the capacity to do functional imaging of blood vessels at any other cross-section. Here you can see another section of the mouse with the spleen, intestines, spinal cord and right kidney very clearly visible without any contrast agents. These images have a resolution of 125 micrometers, and this is even possible in real time with 50 frames per second. You can imagine that this is an incredibly useful tool for preclinical studies, and it offers the possibility to collect both structural and functional data at once in real time with very low cost compared to MRI or PET. Now we move on to a different example, going into the direction of clinical applications. This is the commercial prototype system Imagio. It combines traditional ultrasonic imaging and photoacoustic tomography in a single handheld probe. In the diagram of the probe, you can see the normal ultrasonic transducer in the middle, in the center of the probe, and the optical fibers to the left and the right that illuminate the skin and the target below the skin homogeneously. The main focus of this device lies in detecting breast cancer. To understand its advantage, I give you a short reminder on oncology. When a tumor turns malignant and shows increased growth, it needs a lot of resources since it uses them much more inefficiently than healthy tissue. This draws away all energy from the surrounding tissue. This constant lack of resources in the tumor's vicinity is countered by the body by growing additional blood vessels in this area. which is very fatal, of course, since it only gives the tumor more material to grow. In a very simplified version now, but this is enough to understand this device, at least on the surface. Yeah, so because of this effect, the amount of blood vessels around a possibly malignant structure can give clues whether the structure is pathological or not. And this is what PAI can be used for very efficiently. Here are some examples from the Imagio. These are the conventional ultrasound images from breasts showing dark dots under the skin which might be malignant tumors or just harmless fibroadenoma. It is difficult to judge their danger just from these images. But switching on the PAI images, it is clearly visible which of the potential tumors have above average blood vessels in their vicinity from the total hemoglobin detection images, and which ones deoxygenate their supplied blood too strongly from the hemoglobin oxygenation images. Here one can see that in the two cases on the left, the unidentified spots are just harmless fibroadenoma, while the two images on the right show malignant tumors, which was also verified with other methods as well for these examples of the study, of course. We can conclude that PAI is an incredibly promising field. What I observed is that several groundbreaking innovations from other imaging techniques can be or are already translated to photoacoustic imaging as well. For example, the super resolution from fluorescence microscopy or image reconstruction from sparse data originally developed for MRI, or the usage of dyes and nanoparticles to track certain substances, and so on and so on. So I hope this video was able to transmit some of the optimism of the PAI optoacoustic community. And thank you very much for your attention. The sources of the talk are in the video description, and feel free to use the comments for discussion. And I encourage you to correct any possible mistakes, since this is far from my usual field of research. Have a nice day.